The baud generator. The standard baud rates we'll be using for this design include 115200, 57600, that's 8400, 19200, 9600, 4800, 2400, 1200 bauds per second, and our system clock is assumed to be 14.7456 MHz. Now, an example. Assuming we want to use a baud rate of 115200, so the first thing we do is to divide this baud rate, to divide our clock with this baud rate, that is 14.7456 MHz divided by 115200, which is equal to 128. Remember, for the division, you have to multiply the clock with 10 raised to the power 6. So we need to generate a pulse every 128 counts. Now, oversampling. This is used only at the receiver to minimize error in data reception. This is a sample data bit to be received by the receiver. At the receiver, data reception starts at the edge of the start bit or 0, which is used to wake the receiver. Sampling data at the edge can introduce error because any of the adjacent data bits can be sampled due to slight timing error. So it's best to sample at the middle of the data. So to do this, we need a way to sample the start bit at the center rather than at the starting edge. So for this, we use oversampling. In oversampling, we can sample a single bit 16 times, so that when we receive the edge of the start bit, we can adjust our count to 8 instead of 0. And by the time it gets to 16, we are halfway or at the middle of the start bit. And for every other 16 count, the data will always be in the middle of the received bit. So to get 115200 baud rate, instead of counting 128 as we calculated earlier, we divide by 16. That is, the 128 now becomes 8 multiplied by 16. This 16 will now be used for oversampling. The 8 in binary is counted as 0 to 7. So in the code, instead of using 8, we are going to use 7 instead. Next, the Vcl code. This is the Vcl code for the baud generator. The first part is the vhdl standard libraries. Next, the baud generator port, including the baud select, reset, clock, clear clock, and baud clock signal or ports. Next, the signal, which we will discuss. Next, the baud select multiplexer. Here, different values of the baud select represent different baud rates, and they give different values at the clock counter signal. This is the 7 we calculated for 115200 baud rate earlier. The accumulator register is used to store the first part of the counting. Example, for 115200, the baud select is 7. Once the accumulator counts to 7, it resets and generates a signal which will be used for oversampling. This is stored in the clock 16 register, and this is represented in logism. Next, the oversampling stage. Here, a 4-bit counter called clock 16 counter register counts up to 16 from 0 to 1111 in binary and resets, and this is when our baud clock signal is generated. The clock 16 register signal is used to increment this accumulator. For example, for 115200, the first accumulator is going to count from 0 to 7, that is 8, and the second accumulator will always count 16 for all the bauds due to oversampling. Only the first accumulator will vary depending on what baud rate is selected. That will be 8 times 16 equal to 128. And to verify, 14.7456 MHz divided by 115200 is equal to the 128 we have above. The clear clock signal comes from the receiver, as we've seen from the receiver subcircuit, and it sets the oversampling counter to half the count, or 8, whenever it receives the edge of the start bit. It compares its previous value and makes sure it was previously off using this AND gate. And if it's previously off, it means it's not just a data bit but the start bit. This clear clock signal is not used in the transmitter and is set to 0. It's only used with the receiver. This is the logic behind the baud generator. In our next tutorial, we'll discuss the transmitter.